further introduction, hello, my name is Minseok from Korea University, and in this talk, I will introduce you a new inherently explainable graph machine learning method. Interestingly, this method is developed based on program language techniques only that have been developed in PL community. The title is PL4XGL, a program language approach to explainable graph learning. This is a collaboration work with Jihyeok and Hakjoo. There are many graph structure data around us. For example, molecules, training activity, healthcare, and even a program is a graph structure data. And we do many tasks using graph machine learning methods. For example, some techniques predict whether a program has bug or not, or predict whether a chemical reaction is positive or negative. And currently, the most popular graph machine learning method is neural network-based method called GNN. And I think many of you here are already heard about this technique because it is widely used in practice and actively being researched in academia. But this mainstream method also has a well-known problem named explainability. This black box method does not explain why it made the predictions, and the value of y is growing very fast in machine learning. For example, in some applications like healthcare or fraud detection, explanations are not an option because they are related to human safety. So to address this problem, many GNN explanation techniques have been proposed to provide explanations about the GNN's predictions. And majority of them work in a similar way. After a model made the prediction from a graph data, the explanation technique takes the three components and produces explanations, usually a subgraph. For example, let's say this molecular graph data is given, and the GNN made a prediction that the chemical reaction is positive. Then GNN explanation technique provides a subgraph explanation like this. And this subgraph is saying this graph pattern is the key reason why the model made the predictions. But in this work, currently this combination, I mean GNN with a post-hoc GNN explanation technique, is the mainstream of explainable graph machine learning. But in this work, I found this explanation technique has two, I think, fundamental limitations. The first problem is this explanation technique requires additional, which are usually very expensive, explanation cost. For example, some GNN explanation techniques enumerate possible candidate subgraphs, which should be impractical if the graph data is large. And more importantly, the explanations are not guaranteed to be correct, which means they may not be the actual reason behind the predictions. And I think these two key limitations are very hard to be addressed unless we change the black box. So in this work, we designed a new inherently explainable graph machine learning method without using neural networks. Instead, we designed a new domain-specific programming language named GDL, Graph Description Language. In our approach, a model is a program implemented with the programming language I designed below. So this language is our first key idea. And our model takes the graph data and provides classification results and simultaneously provide explanations that are guaranteed to be correct. And in our approach, the learning problem is formulated as a program synthesis problem. So we designed a program synthesis algorithm that takes the graph data, training graph data, and automatically generate source code for the model. So the program synthesis algorithm is our second key contribution. This slide shows how our model looks like and works with a simple example. In this slide, this is example graph data consists of 4 nodes. And in this graph data, each node has a feature vector. The 2 nodes N1 and N4 have the feature 1, and the 2 nodes N2 and N3 have the feature 0. The blue-colored nodes belong to label 1, and the yellow-colored nodes belong to label 2. And this shows an example node classification model implemented with our programming language. And it consists of 3 triples. And in the first triple, this is a graphical representation of a program in our language. In our language, a program can have node and edge variables. And each variable can have feature value constraints described by vector of intervals. And a program can have target variable, and in this program, the target variable is the node variable y. And this program is describing a node pattern. The semantics of this program is nodes having a predecessor whose feature value is equal or less than 0.5. Our model will classify such nodes into label 1, and the score of the program is 0.8. So in our example, the 2 nodes N1 and N1 and N3 are classified into label 1 because they have a predecessor N2 whose feature value is 0, which is equal or less than 0.5. And the used program is provided as an explanation illustrating why our model made the prediction. The second program is describing nodes that will be classified into label 2. And is describing nodes having a successor whose feature value is equal or less than 0.5. So the 2 nodes N2 and N4 are classified into label 2 because they have a successor N3 whose feature value is 0, which is equal or less than 0.5. The third program is describing all the 4 nodes in the given graph data, which makes a conflict with the second program. In such conflict, our model uses a better scored program for the classification. So the 2 nodes N2 and N4 are classified into label 2 because the second program has a better score. So now, all the 4 nodes are accurately classified, and the explanations are simultaneously provided. I mean, there is no additional explanation cost. And more importantly, the provided explanations are guaranteed to be correct because our model actually used the programs for the classifications. In our approach, the accuracy of the model is determined by the quality of its consisting programs. For example, if we swap the first 2 programs like this, then the accuracy becomes 0. So the goal of the training process is to synthesize high-quality programs and scores that will accurately classify graph data in the test set. To do so, I designed 2 learning program synthesis algorithms named top-down and bottom-up synthesis algorithms. I will not explain the details of the algorithms, so if you are interested, please ask me the question or consult our paper. And in our evaluation, we compared our method with representative graph neural networks like GCN, GIT, GIN, and state-of-the-art GNN extension technique named SubgraphX, which provide subgraph explanations for the GNN's predictions. And we aim to answer these 2 research questions, whether our model is accurate and provide high-quality explanations for the predictions compared to the baselines. The baselines are trained and evaluated using a GPU, while ours is trained and evaluated using a CPU. And this table shows the overall accuracy of our method compared to the baseline graph neural networks for 12 different node and graph classification data sets. And in our evaluation, our method achieved a comparative accuracy. For example, our method shows the best accuracy for these molecular data sets, which are about predicting chemical reactions. But this also shows a limitation of our method. In the largest data set, Hive, which consists of 40,000 of graph and 1 million of nodes, our method failed to finish its training task within 2 days. Time budget was 2 days. But I think it is not a fundamental limitation of our work. If we can use plenty of cores, or we can design a more efficient algorithm, we can finish each training task within the time budget. And our approach provides high-quality explanations which are correct and simple. In this plot, y-axis presents the score of a metric fidelity, which is designed for measuring correctness of explanations. I will not explain the detail of the metric because it is a bit complicated. But in this metric, a lower value indicates more correct explanations. And x-axis presents the score of a metric sparsity. And in this metric, a bigger value indicates more simple explanations. And as the figure shows, our method achieves a far better balance between sparsity and fidelity compared to the baseline. And this tendency also shown in the other data sets. So this is the last slide of this talk. In this work, we designed a new, accurate, and explainable graph machine learning method based on two key PL techniques. The first technique is domain-specific language design for defining AI models. And the second technique is program synthesis for learning models from training data. The evaluation results show that our method achieved a competitive accuracy compared to the GNNs, but provide high-quality explanations for the predictions. So the conclusion is, PL techniques are even useful for AI. Thank you for listening. I'm happy to answer any questions.
Hi, really great talk. I've seen approaches similar to this before where this idea of using a programming language, synthesizing a programming language to replace a neural network, I think is really cool and really great. But I don't have any intuition for when it works better than the alternative. Can you give some intuition as to like why this is a domain where this works, or is there none and it's just we lucked out?
I think our method work well in graph structured data because graph structured data is well structured compared to the vision data. I think our method is appropriate if the data is well structured.
Great, thank you.
Thank you for the nice talk. I was wondering if you could comment on the relationship between your domain-specific language and other graph database query languages like Cypher.
Oh, sorry, I don't know much about Cypher.
So basically, your domain-specific language has these constructs like node pattern matching and edge pattern matching. So that that's pretty common in the context of graph databases and query languages. So basically, think of these as SQL but applied to graph databases. So your DSL looked very similar to a language like Cypher, for example.
Oh yes, our language is very similar. Our approach is very similar to SQL, but sorry, I cannot answer the question because I don't know much about what the language was.
Cypher, but there are other graph database query languages as well. Okay, thank you.
Sorry for that.
All right, so if there are no more questions, let's thank Minseok again.